Hello everybody, welcome to this webinar about our new Xsens biomechanical model, the innovations, the insight, and obviously the impact. We want to give you all a warm welcome. We're very happy to see that so many people have registered for this webinar. First, a little bit about Xsens. For the people who do not know, this year Xsens is actually 25 years, so we are very happy to be able to show to you today on our 25th anniversary year that we have also a new biomechanical model. Obviously, Xsens has been around for a long time and we have a global presence, so multiple offices, over 2,000 customers that use our equipment. And today is again a next step in that journey of us that we want to do at least another 25 years. So a little what is new in MVN Analyze 2025. We try to adapt smarter workflows. Our goal obviously is to make MVN quicker, easier and faster to use. So to do that we did something which we call auto sensor mapping. What it does, it allows you to put the Awinda sensors anywhere you want. Left on right, right on left, and with an advanced calibration it will exactly know where the sensors are, and hence it will basically lower your setup time. We implemented a dark mode for the people who are in darker labs and don't want to be blinded by our previous software. We have a nice dark mode, so new icons that make it easier to use. And obviously, that's why I brought Roelien and Domitille today, we have a new biomechanical model. They will explain everything about it. And like I said again, any questions, put them in the question section, and then afterwards you'll see me back to host a live Q&A.
All right, thank you. And yeah, welcome all of you. We are very happy to present you today the new biomechanical model, the changes we made, and also the rationale behind it. However, before we dive into what's new, let's quickly revisit how we get to such accurate and reliable data in the first place. At the core of our system are inertial and magnetic measurements unit, which, as you may know, measure acceleration, linear acceleration, angular velocity, and the Earth's magnetic field. And unlike optical systems, it does not measure directly the absolute position and orientation in the global space, which brings us to two well-known challenges: the magnetic disturbance, which can degrade the heading accuracy, and of course, the integration drift. And this is why over the last decade, we've addressed these issues and limitations with a multi-layered solution, combining advanced sensor fusion algorithm with biomechanical and physical modeling to achieve magnetic immunity and drift-resistant motion tracking, even in complex, uncontrolled, or magnetically disturbed environment. And it all begins with our sensor fusion engine. Each sensor performs high-frequency signal processing using our patented strap-down integration algorithm. And these algorithms run internally at around 1 kilohertz, preserving then the motion dynamics, even when outputting data at lower rates, as you may know, with our link system at 240 hertz and the Awinda at 60 with the full body system, or at 100 hertz with the lower body. And this ensures that critical signal fidelity is then maintained and fed into our models. Our model, the biomechanical model, 23 segments, 22 joints which are following the ISB recommendation. With 17 sensors, 17 segments are tracked directly. The remaining 6 are estimated through our engine. And to ensure high motion capture fidelity, we also incorporated a soft tissue artifact model. Indeed, the connection between the sensor and the corresponding segment is not a rigid one, as it may fluctuate depending on the amount of soft tissue movement. Hence, our sensors are modeled as loosely coupled to the bone to simulate and account for that movement. And on top of that, we have, of course, our sensor to segment calibration to map accurately our sensor to our segment. And as you may know, this is a critical step to have accurate data, as it enabled to have the initial segment orientation and to map that with our sensor. Further models, of course, layer are included, such as, well, the floor contact detection, or magnetic immunity, and also integration drift compensation. All these models, they operate in real time, enabling robust, full-body 3D capture motion in a variety of movement, and so anywhere. On top of that, we also have an HD reprocessing, which leverages them the same data, but with more computational resources, enabling enhanced accuracy, particularly for complex motion, as you can see on the video with ground contact with the push-up. You see a difference between the live and the HD process and the foot contact. Altogether, this engine enabled 5K capabilities, hard to achieve. The multiple contact points, but also magnetic immunity, drift-free orientation, multiple person tracking, and a 3D position estimation. And this robust system allows us to deliver laboratory quality data in real-world field conditions. And this is the software that you know and may be familiar with. So why did we update our biomechanical model? Why did we start here? Well, our biomechanical model is one of our core technology. And right now, our legacy model, like many in the field, is built on generic anthropometric data, primarily derived from male cadaveric datasets. While this is standard practice, it presents significant limitation. When applied to an individual with different body types, like female users, systematic inaccuracies emerge and may then impact critical output, like segment properties, joint angle, segment position, orientation, balance, which then would, of course, impact the kinematics and any other analysis that you would do on top of these. And all these outputs then may also impact the objectivity of the assessment which then goes into an ergonomic, walking, but also more dynamic motion like the drop landing, or also in clinical and rehabilitation for musculoskeletal diagnosis. And we capture movements. So these anatomical particularities are important for us. These discrepancies we want to avoid. And this is why we have Biomech 2.0. And it's true that regarding body dimension, well, we already allow users to manually customize this segment length to better match individual proportion. This approach, we know, has some limitation. It can be time consuming, and it relies on anatomical landmark expertise from your side, and it also means that it's prone to user viability. And most importantly, it is regarding the body dimension, but not the properties. So inertial properties such as mass distribution, center of mass, still are based on male references. And this limitation really underscores the importance of having biomechanical models that represent both male and female anatomy, which is why we have now Biomech 2.0, a male and a female model based on living data sets. Of course, these data sets come with an average height, and then we rescale them linearly to a 170 human model, which is the one that you have now in the new software. But this is not all, because Biomech 2.0 is not only regarding anthropometric data. We also update and refine the spine model. With only 2 sensors on the spine, on the pelvis and the sternum, we use a spherical linear interpolation to estimate the motion in the untracked spinal segment. From there, we improved the model in 2 key ways. First, we updated the segment's length to accurately represent the thoracic and the lumbar proportion. Then, of course, we look at the physiological behavior. The human spine transitioned from an S to a C shape while bending. As you can see on the graph, the proportion between how much the pelvis accounts for this, the thoracic and the lumbar, differs. And it differs along the bending and the flexion. This is why we refine our function in 2 ways. First, we adjusted the slurp weight ratio, and then we added on top of that a gradual function. All these result now in a new spine function, which is physiological, have a more physiological behavior with an S to a C shape, and then represent the well-known lumbopelvic rhythm. Today, we are very happy to introduce you, this is Biomech 2.0, the latest evolution of our motion analysis system featuring anatomy-specific male and female biomechanical models. And with Roelien, we will walk through the validation study comparing these new models against our legacy system and optical motion capture showing enhanced accuracy across a variety of tasks.
Yes, so today we will present you the two new biomechanical models which represent male and female anatomy specifically. We will here go over the whole validation procedure as we published in our white paper. But first, I want to explain some naming conventions we use. So at the left side you have our legacy model. This is the model you already know from our previous software versions as well, and we refer to it as BM1, Biomech 1. This one is also still available in the 2025 versions. Then on the right side, you see the new biomechanical models, a male and female version, which is called the BM2, Biomech 2. So, okay, how did we objectively assess the performance of our new models? For that, we used our MVN models against optical motion capture systems. So on one hand, we had our full body Awinda system, with 17 sensors, which runs at a frequency of 60 Hz. We measured all body dimensions, and then all body dimensions were measured also by the same person to avoid inter-operator variability. Then the body height and the foot length we used as input for the scaling of the rest of the model. After this, we did an end-post plus walk calibration with some additional checks, for example, in the inter-hand distance and the inter-feet distance to assure the quality of our calibration file. At the end, after all recordings, we did the reprocessing, used the HC reprocessing. On the other hand, we had our optical motion capture system. It was a quality system with 15 cameras, and we put 43 reflective markers according to the sports marker set. These markers were placed on top of the skin as much as possible on bony landmarks to avoid motion artifacts as much as possible. But for that, it means that we could not use our Xsens Awinda shirt and the gloves, so we taped the IMUs on top of the body. We initially started with a static A-pose recording, which helped in labeling. Then we had an anatomy-specific scaled OpenSim models, a female and male specific, which afterwards we used the inverse kinematics tools to get the joint angles. Okay, so in this validation procedure we had 11 participants, 6 male, 5 female. We asked them to perform motions which were specifically for the upper and lower body. For the upper body, these were the arm raise and clap, as you can see in the figure, and we had the spine bending. Then for the lower body, it was walking back and forth on a self-selected speed, and the subject performed squat jumps. We divided then the analysis in 3 different ways. For the upper body specifically, then the lower body, and we also did a full body analysis on body dimensions. So specifically for the upper body analysis, we had on one hand the arm raise clap motion, as you can see in the video. We extracted all clapping events, so above the head and in front of the body, and we calculated the Euclidean distance between the hands at those specific points. We calculated them for the optical system and for MVN, both the legacy models and the new one, and we calculated the error between the systems in centimeters. Then to get one overall accuracy metric, we also calculated the root mean squared error. Then on the other hand, for the upper body, we also had the spine bending. Spine bending was 2 cases. We had, first of all, the ground reaching accuracy, in which we took the point at the wrist. And for the second part, we also took, to really assess the spine flexibility, we took the acromion point. For both points, we took at the lowest point of the bending motion, we took the distance between the point and the ground. Again, we calculated the error in centimeters between MVN and optical, and we had one final metric, the RMSE. Then we go to the full body analysis. Here we used all measured body dimensions. So, as you might know, if you fill in body height and foot length, MVN automatically scales the rest. So that's what we did. We filled in body height and foot length for the new model, either the male or the female, depending on the subject. And we filled in the same for the legacy model. Then we compared the automatically scaled other body dimensions to our measured ones. And we presented this as a percentage difference. Then for the low body, we had, as I already said, the squat jump and walking at a self-selected speed. For both motions, we calculated all the joint angles, and we compared them between the OpenSim new model, so BM2, and also our legacy model. Then for the walking on self-selected speed, we also calculated the spatial temporal parameters like step width, step length, and here we used optical versus BM2 versus BM1 because we didn't need, we just could take the optical marker from the heel. Again, for both, we had the root mean squared error as a final metric. Okay, so how does the new model compare towards our legacy model and against OpenSim? Let's go into the results. Here we have first the full body analysis, shown as a scaling performance. In the graphs, on top you see all participants, in the middle it's just the male, and on the bottom one it's just the female. At the y-axis you see the percentage error between our scaled version of MVN and the measured body dimensions. On the y-axis you see all the scaled dimensions, and in blue you see legacy model, in red you see the new model. So let's go over this one by one. We start with the shoulder width, and as you can see it's kind of an equal performance. The legacy model is a bit above the 0 line, the new model is a bit below the line, but on average it's 1% overestimation, 1% underestimation, so kind of equal. Then we go to the shoulder width. Here again, if you see, especially on the old participants, it's kind of equal, except that the new model, so the red bar, has a higher consistency. Then we jump a bit, we go to the hip height, and here we see that actually our legacy model was a bit more accurate than our new models. However, one thing to keep in mind here is that for the hip height you need to measure the greater trochanter, which is kind of a hard landmark to palpate. And this error we see here, the 2%, is within the range of human measurement errors. So, albeit the difference, we take it, it could be in the measurement error range. Then we go to the knee height. The knee height, again, especially on the average, they are kind of equal. The female performs a bit better than the legacy, male performs a bit worse than the legacy, but on average they are kind of similar. And then we go to the ankle, the knee height, sorry, that was the hip width. Now we go to the knee height and the ankle height. As you can see, they both improved, the knee height by 1%, the ankle height even by 10%, but of course ankle height is not that much of a distance, so 10% it's about 1 centimeter, but it's really consistent about all participants. Okay, this is of course all nice information, better most of the times, equal in some cases, but now we come to the arm dimensions. And here is where the actual improvement is. Because in the arm dimensions you have the elbow span, the wrist span and the total arm span, and as you can see they all improved significantly. The error is reduced by over 50%. And of course this is what we expect to also impact the other upper body kinematics, like grasping, reaching motions, these kind of things. But we'll see in the next checks. So we go to the upper body hand clap motion. On the graph at the top you see again in blue the legacy model, in red the new models. On the y-axis it's the error in the distance between the hands, and on the y-axis, on the x-axis you see all participants, where F stands for female and M stands for male. And as you can see, our previous model, the legacy model, had an error of average 4.6 centimeters, while our new model has an error of average 5.6 centimeters. And I hear you thinking, okay, but you just said it should be better and it's 1 centimeter worse. True, I will come back to that later. Since if we check the lower graph, the clapping in front of the body, you see actually a huge improvement. We had initially an error of 14.8 centimeter for the legacy model, while now in the new models this reduced to 8.5. This is an improvement of over 40%. Then we go, why is this the case? Why did we improve better for the clapping in front compared to clapping on top of the body? Well, here it's an interesting thing, because in Xsens Analyze, we model the shoulder as a rigid connection between the spine and the upper arm. And for the people who might know, the shoulder is quite a complex joint. So it is not just a ball and socket joint, but we also have the scapular motion, which comes into play when you elevate your arm. And that's the thing what happens here. So although we improved way on the arm dimensions, if you might have seen, were still slightly overestimated by a few centimeters. And if you then clap above your head, you can use this extra arm length to compensate for your scapular motion, which is not there. That means that actually you come closer. But then we clap in front of the body, our scapular motion is way less because we don't elevate the arms that much. In that case, as you can also see in this figure, you see that the overestimated arm length indeed makes that our arms are a bit crossing. And that's then the difference between why we improved for clapping in front so much and the improvements not that much above the head. However, we only measured on 11 subjects, as I already said. And we actually did first measurements on 20 subjects. However, in phase 1, we split it in 2 phases of measurements, and after phase 1, we had to make a slight update to the model, so we cannot use and present all the data of the 20 subjects. But what we did see is that the hand clap on top of the body over all 20 subjects was kind of similar. It even improved a bit. So what we think is that this is kind of equal performance, which will cancel out if you use enough subjects. And that's why we highly encourage you all as users to prove this and see if it's really worse or if it's actually better what we would expect. Then we go to the other part of the upper body, the spine bending. So on the top graph, you see again the 2 models against optical. And we have here the wrist to the ground. So during the most bending, when the arms are closest to the ground, we take the distance between the wrist and the ground, and we calculate the difference with optical. So you see at the left that the models kind of perform equal, which was a bit strange in our opinion because we refined our whole spine function. So if you refine a spine function, you would expect your bending is better, you would expect your arms are closer to the ground. But then we thought, okay, but we also had a huge difference in arm dimensions. Is it that because we now have shorter arms, we do compensate by the spine, but there is less arm length, so it comes less to the ground? And indeed, if we fill in all body dimensions, it is indeed a huge improvement of 3 centimeters. So we're 3 centimeters closer to the ground with our new biomechanical models. But then still we have the arms in it, so we wanted to assess actually the performance of the spine. And for that, we did then also the acromion point to the ground, which as you can see, indeed the new models are way better. And also in that case, if you fill in body dimensions, you still see this improvement of a few centimeters. So yes, we can still say we have an increased range of motion in our spine. Okay, the final part of the analysis is about the lower limb, lower body. Here we mainly focused on the joint angles because we didn't do huge model updates, and we actually mostly wanted to assure that the joint angles between our legacy model and the new models weren't that different. Actually, they should be kind of the same. We only changed segment lengths, and as you might know, segment lengths should not impact the joint angles. And this is indeed what we can see. We have a high correlation coefficient of 0.98 for both the gait and the squat jump between both legacy and the new biomechanical models. So that's also what you see in this table. It's not just a copy from BM1 to BM2. There are slight differences, but they're so minor that I can imagine you maybe don't even see them. And this indeed holds the same for also the squat jump. It's just to show you the table, but indeed, as already said, the correlation coefficient is really high. It's above 0.98, so they are the same. But then, of course, it's the same as legacy, but we also had the open sim to compare to. And here you see a moderate correlation of 0.57. And in the next slide, if you go to the gait, this is even worse, and we have a correlation of 0.31. How can we explain this? Well, as you might know, we have different models in OpenSim and in MPN. So a different rotation center of just a few millimeters could already cause a few degrees of difference. Okay, nice explanation, but how do you know for sure? And that's where, luckily, our previous colleagues already thought about by publishing the first MPN model. Because then they applied all the initial pose, so the initial calibration pose of OpenSim towards our MVN. And in that one, you can read more about it in the previous white paper, but in that one, indeed, they saw the differences were way smaller. So we do know that those differences do come from having a different model. And by showing that our new models are the same as our legacy, we are sure we're still having the same good quality. And then we go to the spatial parameters. It's a huge table, I can imagine. It's a bit impressive, but on the top you see the distance in centimeters. So you have actually 3 columns, length and width for all subjects, then in the middle length and width for the females, and at the right the foot length and step width for the males specifically. On top we have the optical one in bold, which is the one we compare to. And what we see is that we have overall a gain of 0.5 centimeter, and for female it's even 1 centimeter. And we also have, if you fill in all body dimensions, indeed over all subjects, a gain of 1 centimeter, which is quite a bit in step length and step width. But then if we focus on the new models and then also fill in the body dimensions in our new models, then we see it even improves more. So if you want really accurate step length and step width, then fill in all body dimensions in our new biomechanical models, and you will really have an improved accuracy. And then I hear you thinking again, okay, 1 centimeter better. Why is that then so much better? Because again, on these 20 subjects, which we cannot present everything from, but we knew the model did not impact that much, we see it was even better and the improvement was more than 1 centimeter. So here we are confident to say that this won't cancel out by having a lot of subjects. Okay, now we already come to the few final slides by showing some key improvements. It was a lot of information, so let's just highlight a few key improvements to wrap up. As you already know, we had a male and a female model with all different body dimensions, and indeed that is the most improvement. We have a 50% improvement in arm dimensions, which results in an overall performance improvement of clapping in front of the body of 40%.
Then we have, of course, a new refined spine model. And as you saw, it has a way more physiological behavior, but also an increased range of motion with the shoulder to ground distance increasing by 2 centimeters.
And then we have the step width again. We have a gain of 0.5 centimeters, and if you fill in all body dimensions, this is even 1 centimeter over all subjects, which is amazing in any kind of gait analysis.
And then, of course, altogether, incorporating, as we said, the subject-specific body dimensions significantly improved tracking accuracy and consistency. This is especially valuable for clinic, ergonomic, robotic application where precision is crucial. So, yeah, with the release of Biomech 2.0, we have taken a significant step forward in advancing motion capture, making it more anatomically accurate, objective, and inclusive. The new anatomy-specific model outperformed the legacy version on key dimensions, particularly in upper body kinematics and arm skilling, where precision matters. And when combined with the subject-specific body dimension, they enable assessment that are more personalized, more reliable, and physiologically faithful. While of course further development is ongoing, our focus remains advancing motion fidelity, improving physiological behavior, and broadening the depth of available data. Biomech 2.0 is more than an update. It is a new foundation built for consistency, scalability, and real-world application adaptability. It reflects our commitment to developing technology that transform movement into meaningful and usable data for you. Whatever the application, clinical, sport, ergonomic, or robotic, we strive to give you the ability to capture, understand, and act on movement with confidence in new way and in any environment. And yes, all details and the validation metrics are available in the white paper, so feel free to reach and have a look at it. And we are really excited to see how you're going to use and apply Biomech 2.0 in real world, in research, clinical practice, and in ergonomic. Thank you all.
Perfect. So I brought my laptop so I can see all the questions here. So that's why I will be looking up and down. First, thanks again, ladies. Really nice presentation. There are a few questions in the chat. Some of them I've already tried to answer. First thing I want to say, some people were asking about, is it possible to see a live demonstration or see the real-time parameters? Obviously, yes. We would be happy to get in touch with you, set up a live demonstration, go through all the software options we have, not only the biomechanical model, but some other stuff as well. So feel free to reach out to us. The best way to do that is to send an email to sales@movella.com. And from there, we will make sure that your questions will be distributed to the right account executive within the company, so that the person in your region would be able to help you in the best way possible. So I'm going to pick out the questions we have here. One of the first questions I saw from people is it actually possible if I have a recording that I made, for example, in Xsens 2023 or 2024, can I reprocess that data into the new biomechanical model?
No, that is not possible.
Okay.
Because the recording was done on the legacy version of the 2024. It is possible to reprocess it in 2025 in the update, but it's still going to be in the legacy version.
Yeah, exactly, exactly. So you can do the legacy version in the new biomechanical model, so to say, but
in the new release.
Yeah, exactly, in the new release, but not for the male or female.
No.
Okay, thank you.
Then you need to record it indeed in the
exactly,
new,
exactly. I hope that answers the question. There was a few people there. So I believe that's clear. So let's see. I'll go down here. So somebody was asking if they recorded data with the MT manager, so only the raw sensor data, if they can input that information into the biomechanical model. So what is basically, in order to use MT manager data, it's only the raw sensor data. And that's also why we have that software available for free. So basically you can just see our sensor data and use the algorithms that are on the sensor, but that's it. If you want to use the new biomechanical model or many of the other features we provide in our Xsens Analyze software, it is something you have to purchase from us. Because in the end, Xsens might sound strange, but we are a software technology company. The IMUs is actually very basic technology. Everybody can make a PCB, a battery, and the 3 components on it. But making that work in a biomechanical model and making that work everywhere as we stand in the lab or outside, that's actually what we do for 25 years. Yep. So if you want to have access to that type of the software, then feel free to reach out to us. We'd be happy to share trial licenses that you can try it out yourself. But getting MT Manager data in Xsens Analyze, unfortunately, that's not possible. Then I will go more into a in-depth question that I am not able to answer. With the new biomechanical model, does this fix the hand clipping through each other when performing a clap, when using the height and foot measurements, or is it still only fixed by inputting all the other biomechanical dimensions as well?
No, the results I showed is really just with filling in body height and foot length. So all the information of hand clapping, or if I did not specifically say we filled in all body dimensions, it is all based on the scaled version, body height and foot length as input. Because in the end, that's what most people use, right? So you want to know the information or the accuracy on that level.
Yeah, okay. Yeah. So
this improvement is really on just filling in.
Yeah. So if we do like a thought experiment, let's say I put in super highly accurately all body dimensions, then it could even improve more.
Could, yeah.
Could, yeah.
Yeah.
Okay. We didn't test that yet, but that's something that is then clear as an answer on this question. This is a question from Wendy. She said, if you know the structure of the error in the model of the performance, why not introduce a correction, at least to center around the zero? So if we already know the error, but it probably is not a fixed error, right?
But it's not a fixed error, so
Yeah.
it's really hard to say indeed to correct for a kind of offset, because what we see is just the average over 11 subjects. If you would take even more subjects, the error could be different. And for some people, it is highly accurate. So if you then would apply an offset, it got worse.
Yeah.
So that's always a bit hard. Yeah.
Good. Okay. It's a good question, by the way. Thank you.
Definitely.
This was a question about, somebody was asking about the population of the study. So if we could define the male and female anthropometrics models, what were the characteristics like age, ethnicity, sports or general? What did we use for our sample?
For the new Biomech model, they are based on literature data, and it's always healthy Caucasian people. So young, between 20 to 40 years, and of course healthy participant. The fact that they are Caucasian already slightly restricted. Male, it is 31 male, and female is 46. For our validation, it is something very similar. The 11 participants are colleagues here, so it is also again healthy and Caucasian mostly participant.
Thank you. A good question from Ko Sasaki. She asks, does or how does Xsens IMUs and the software avoid a gimbal lock problem?
Well, the thing is, gimbal lock occurs only when you use Euler angles and not when you have quaternions. So inside our calculations, everything, we do everything with quaternions, and then only for the output we show also the joint angles in Euler angles. And for example, especially for the shoulder knee, the gimbal lock is a huge problem. And that's why we provide two types of order of rotations in our software output for the joint angles, but you can still also access the quaternions yourself via the MPNX output export. So if you're interested in the quaternions, you can use it themselves and set them to Euler angles or do anything with it what you want.
Cool, thanks. A question from Corné Dijkstra. Have you performed a statistical analysis on the biomechanical models to prove if the differences are actually significant, for example, a repeated measures ANOVA?
We did do indeed the t-test on it, and we had, so indeed if we say it's better, it is a statistically significant difference. Yeah.
Cool, thank you. Aitor, he asked if we have integrated finger tracking in the same structure as the rest of the mannequin, or are the Manus gloves still separate part, specifically in the MVNX files? So, yeah, you partially answered the question already in your question. Basically, Manus has developed their own biomechanical model specifically to the hand. So, as Xsens, being a different company, we don't influence how they apply their biomechanical model to their data. We only have influence on how we do it, and we work together with Manus on basically the wrist joint angle, where we use our sensor and the sensors obviously of the lower arm to calculate our own wrist angles, but all the finger data is still in the Manus biomechanical model. Then I have a question from Barry Johnson. What sort of robot applications can this be used for? So it's actually a very good question, because what we see at the moment, there's multiple. We have people that train one-armed robots. We have people that use our data to stream live into robots for teleoperations. We see people using our data to train AI models that are executed in robots. So what I would ask you, Barry, please contact us, and we will be able to set up a meeting with you, and we'll explain everything more in detail and show you what's possible. This is one from Daniel Levine. He asked, if you sync with force plates, do you have any data on how accurate obtaining joint reaction moments via inverse dynamics? Also, is the high fidelity reconstruction performed using vector graphs or the equivalent of an RTS smoother?
For the first step, I could say, well, you need to know, to have joint moment, you need to know where your foot is positioned on the force plate, and it means that the force plate needs to be on the same reference system as our Xsens system, which right now I think that the integration is kind of low level and might not be there actually right now. For the next question, I admit it is a very good one, and we can park it now and look at it later and come back to you about an answer regarding that.
Good one. Then another question from John. He says, for real-world application, clinical practice, it needs to be seamless with few operations required, like a point-click solution. How much quicker is it to get from sensor application to data collection?
I mean, that's especially the part with the ASM, right? So it's not really related to the Biomech model. That does not make anything faster. But the ASM, indeed, you need to do some extra motions in the calibration. But for the rest, in the whole setup, you can place any sensor just anywhere. You don't have to check that. So that will fasten it up quite a bit.
I did a time trial
you did? Okay, cool.
2 weeks ago. It's not an official one, which I recorded both sessions, and obviously I have some advanced usage before, almost 5 years, so it's not a real objective trial. But definitely you're able to set it up within 5 minutes. And most of that time is dedicated, like Roelien already said, like applying the sensors to the body and strap them up. The calibration itself is only a 10-second procedure. So, and with this new ASM, we try to even downsize that time of applying the sensors even more. So an experienced user, you definitely be able to set it up within 5 minutes. Then it's a matter of you press the record button, data is recorded, and afterwards we want to implement it that way that you press another button and you have, for example, a gait report. So that's what we want to create, especially for clinical applications. And feel free to contact us, John, because I'm also happy to spend a lot more time on this with you, but it might not be good for the rest of the audience. Then we have a question from Paul. Are there tools or APIs to integrate Xsens into a musculoskeletal simulations platform?
Yes, there is a direct link with OpenSim, which is called OpenSense. And it's already, and also in our webpage, I believe there is a whole documentation for you to follow the different steps and put our input into the OpenSim model.
Yeah.
Okay. And then
You can use any model. It's
like
just
anybody, is that also the same, or is it different?
No, but OpenSense is the same as OpenSim. It's a
Okay.
free software, but
Perfect.
it's just the IMU version of OpenSim.
Yeah.
You can also use all the models you're used to have in OpenSim already.
Yeah. And this is a nice question from Paul, actually. He asks if the IMU has to be placed in a specific orientation, or can we just place it in any orientation when applying the sensor?
The place where you place it is really important, but how you orient, of course, we normally put it in a length or in the width, but that's mainly covered in the calibration. But the
Yeah.
position where you place it, that is still highly important.
Yeah, so to give you an example, Paul, sorry, if I place the sensor on my upper arm, it doesn't matter if I place it over here, over there, or over there.
It does.
However, I won't place it on the biceps, because if I move my arm, obviously my biceps, it will wobble and create sensor data that you don't want to have. So that's why Roelien says orientation, if it's upside down or anything, that doesn't really matter, but where we place it, that's super important. But we have a very nice also webinar tutorial where one of our product specialists actually goes over this setup procedure and explains in detail where to place the sensors for the best outcomes. So I would advise go to tutorials at tutorials.movella.com, sorry, and then you can find all these type of information, or again reach out and we can send you these recordings. Another question. We are from Joseph. We are planning to research package handling, and I'm wondering whether your hardware, our gloves and software can support such research. Specifically, does the software support analysis and comparison for ergonomics? And where can I see the functionality when this was recorded? So, yeah, from my, we do a lot of human factors research. So we have a lot of labs that use the Owinda system or the Link system together with gloves or any type of finger recognition data and combine it in research. So yes, definitely possible. I see another question. Matthias, he asks, does the new Biomech 2.0 affect the risk reporting the ergonomics, especially if we have male vs female? It's known to be different in outcomes to predict physical overload. More potential to analyze on the ergonomic domain. Thank you.
Well, this is interesting. It depends on what you want to assess in this ergonomics, of course. If it's mainly about the joint angles, for the lower body we showed they are not that much different. But if you also want to, for example, have the bending and the reaching, that also is an assessment in general ergonomics report. That, of course, is impacted by having this male or female model. So yes, it can have the impact, but it depends on which measure you want to take or want to use for your assessment.
Okay, I think we're through all the questions.
Cool.
Okay.
Nice.
First, I want to thank you both for presenting today.
Yeah, sure.
It was really nice. I enjoyed it, and as we can see from the questions, there was a lot of interaction. So thank you everybody for putting in the questions, and we hope we answered them to the best of our abilities. If not, you know where to find us, and then we would be happy to come back to any questions you might have. You can go to the webpage for more information. We have a complete base at movella.com page where all the in-depth biomechanical stuff is all explained. And yeah, so we hope that this was learnful and explained the new biomechanical model today. And if you want more information, contact Xsens and we would be happy to help you. For today, thank you for attending this webinar. Spread the word to the people who didn't watch it or were not able to join, and the recordings will be posted online as we already mentioned. So thanks again, and yeah, we hope to be in touch with you guys soon.